Hi, so for today we are going to talk about stress and strain. This is a part of our tutorial about strength of materials. So this is my very first video about strength of materials, and we will be continuing discussing this all throughout the from the first lesson up to the last lesson. So I hope you guys could bear with me and you will watch all the videos about this tutorial. So let's get started. So the very first thing that we are going to take note in strength of materials is the first lesson is all about the stress and deformation, elongation, strain. Okay, we have also the uh, Hooke's law. Okay, but for today's video I'm just going to discuss what the normal stress and deformation as well as the normal strain is. So in this video, okay, we define stress as the force per unit area. So in this case, we'll be having this formula, okay, and this is considered as stress in strength of material, and P is actually the force in Newton, and the A here is the cross-sectional area. So simply, the stress is the force per unit area. So if that is force per unit area, in terms of SI unit, the unit of force will be Newton all over area, let's say in square meters, okay, and that will be equal to the equivalent unit, SI unit of stress, which is pascals. So denoted as PA. So whenever we see PA, or Pascal, that talks of stress. Okay, so simply it's the force per unit area in a normal stress. So for example, we have here a simple metal bar that is uh, has a two force member. So this will be the cross sectional area, and if we pull this, okay, pull meaning we apply force here on the top of the material, and we apply force here on the bottom of the material. Of course, we are applying tension. So this material will be elongated, will be much longer if we apply force. However, the opposite is the same. So if we try to pull, for example, put a force, okay, towards this object, okay, that is compression, because we are literally compressing the material by applying a certain stress or a certain force on the cross-sectional area of the material. Okay, so basically that is the normal stress, force per unit area. And we also have the normal strain, of which we define it as this formula: deformation all over the L. That's the strain. So usually the strain is we'll be discussing it on the latter part of this topic, module number 1, all about stress. And what I would like to emphasize here is the normal stress. We should take note of that, and the deformation. Now let's talk about deformation. Deformation is simply the amount of length, okay, that is deformed. So for example, meaning if we try to pull this material, after some time, because of the pulling, it will produce a certain deformation, and that elongation, we call it the deformation. Okay, so it will be deformed by some little amount. Okay, this is exaggerated, this is too long. Okay, so when we talk about elongation or deformation, it's just simply in terms of millimeters. Okay, it's very small. Okay, to the point that sometimes it's not even visible, but there is an elongation or deformation. So we also have the Hooke's law, in which it states here that the stress is directly proportional to the strain. So the more stress we apply, the more strain that we have, and vice versa, because of its direct proportionality. And we have here the letter E as the proportionality constant. We call it as modulus of elasticity. So every material has its value of E. Okay, certainly it's given sometimes in the problem. Okay, and the deformation, we can solve it by PL all over AE, where P again is the force, where L is the length of the member being compressed or being pulled away. That's the length. This is P in terms of Newton. This is length in terms of meter. Cross-sectional in terms of square meter. Modulus of elasticity in terms of pascals or gigapascal sometimes. So it's given. It's a constant. So another mnemonic so that we can remember the PLAE formula. I learned this from my college days during the board exam. We can what do you call this? Have a mnemonic about it. It's praise the Lord anywhere, everywhere. So praise the Lord anywhere, everywhere. That's another mnemonic. So if you have other mnemonics other than that, then it's okay. So my other classmates also suggest let's play whenever we talk about deformation. Okay, so PL all over AE. So it depends on us on how we are going to memorize these formulas. So but I've given you just some mnemonics about it. So now, having said that, we already know stress, the strain, and the deformation. Again, our focus here is the normal stress and deformation, how we are going to solve problems using stress and the deformation. So let's get started. So for our problem number 1, for the bars shown in the figure below, determine the normal stresses in different parts. So we have here parts AB, parts BC, and parts CD. So we are going to assume, okay, that the diameters of AB, okay, let's say the cross-sectional diameters of this AB is 20 millimeters, the same as the diameter of CD. So this would be our DCD and diameter. So if we speak of diameter, we know that that is DAB. It's 20 millimeters. Whereas the diameter of BC is much, we can expect it's much greater. Okay? So it's much greater. The diameter of that would be DBC equals 40 millimeters. Okay? So, and determine also the total deformation. So in this case, we have seen that this object is being pulled out, okay, by 21 kilonewton and 10 kilonewton, and we have an internal force here 16 and 5 kilonewton. So we are going to recall here in order for us to solve the stresses. So the thing that we are going to solve here is the stresses, okay, experienced in member AB, the stresses, okay, the stress experienced in BC, and the stress experienced in CD. Okay? So in order to do that, of course, we have force in AB. We have to determine the force. Okay, in AB, all over the area, cross-sectional area in AB. And PBC here, and cross-sectional of BC. But of course, for CD, let me just rewrite. For CD, stress in CD, we have the force in CD all over the area in CD. Okay, so we are given the diameters. So simply the cross-sectional area of this is considered as a circle. Okay, so just a circle. So the area of the circle would be in terms of radius pi r squared, or in terms of diameter, that's pi d squared all over 4. So in this case, we're going to use this. Okay, but take note, we have all to convert the millimeters in terms of meters before we can use the what they call this, the formula, because all of those are in terms of square meters. Okay, so let us start. So first one, we are going to have a free body diagram. Of course, we need to have an FBD. So in AB, we can see that if we do that, we have A here, we have B here. Okay, the short thing about AB is that we have a tension, or we have 10 kilonewtons here. And of course, this whole body is in equilibrium. So meaning it's not moving. Okay? So that's one thing that we are going to deal with the statics, or the strength of materials. Statics, it's not moving, but in strength of material, we are going also to assume that these are not moving, and therefore the forces acting on it should be equilibrium, should be zero. Okay? And now, the only problem is we are not going to treat these objects as rigid. So it means that we are going to treat this as deformable. So that's what we are doing. Actually, we are trying to find the deformation. So it's not rigid, but it's deformation, deformable. So if I have this, okay, A and B here, if I just cut, okay, a portion of that, labeled as A and B, or even here in A and B, get the free body diagram, I know I have a 10 kilonewtons, okay, on the other side because of this. And also I have another force, of course. I should have a force of AB, okay, experienced by the points A and B on the right side. So if I get the summation of values of f of x, I have FAB minus 10 kilonewtons equals 0. Okay, so technically my FAB would be 10 kilonewtons. And kilonewtons is 10 times 10 raised to 3 newtons. Okay? That's my FBD for AB. Now, how about for, let's say for BC. So it's very important. So if I have a BC here, okay, I have my BC here, I have my FBD, oops, and then I have, sorry, I have to redraw this. So if I have BC, so I'll be having here, okay, I'll be having a figure like this. So this will be my BC. So I'll be having 16 kilonewtons, and then I'll be having 10 kilonewtons here. So according to our diagram. Okay? So in other words, if I do that as FBD, I have 10 kilonewtons here because of this. And I have another internal here, BC. I have 16 kilonewtons. And of course, I also have another force balancing out these two forces. And that will I call FBC. So if you get the summation of that, I'll be having FBC minus 10 kilonewtons minus 16 kilonewtons equals 0. After all, the summation of forces should be 0. Okay, so because it's equilibrium. So if I have FBC here, I can get 10 kilonewton plus 16 kilonewton. So I have 26 kilonewton. Okay? For the force of FBC. Okay? So and lastly, for letter C, I have CD. Okay? So I have CD. So if I do that, I have here a 21 kilonewton. Okay? A 21 kilonewton here. Okay? I have a 21 kilonewton there. And I also have a force balancing out this member CD. And that will I call FCD. So the 5 kilonewtons will not be included. Okay? So it will not be included unless, okay, we have AC. Right? But we don't have AC, so we only have the B and C. So we are going to get again the summation of f of x here. That would be FCD minus FCD because it's going to the left plus 21 kilonewton equals 0. 21 kilonewton is going to the right, so it's positive. So I have 21 kilonewton equals FCD. So in other words, my value of FAB is now visible. Also, the value of BC is 26 kilonewton. The value of CD is 21 kilonewton. So, I'm now ready to get the stresses in AB, BC, and then CD. Okay, so let me just try to solve this. So if you solve that, okay, the stress, I'm going to rewrite it here. Stress in AB should be force in AB all over the area in AB. So again, if we do that, the force in AB is 10 kilonewtons, which is here. So you have 10 times 10 raised to 3 newtons. So, of course, it's in kilonewtons, you have to times 10 raised to 3. All over the area of AB. So, I have a DAB of 20 millimeters. That's the diameter. So, 20 millimeters in terms of meters, converting it in terms of meters, will be 0.02. Okay? So, I'll be having a formula of pi d squared all over 4. But the diameter is now converted, should be converted to meters. So, that would be 0.02 squared all over 4. So, that's the area. Okay? That's the area of the AB. So, the cross-sectional area. So, as you can see, if we do that, that would be 31.83 times 10 raised to 6 pascals. Or we can have this as 31.83 megapascals. So, this would be our answer for the stressed AB. Okay? For now, that will be our answer for the stressed AB. Alright. So, how about for the stress BC? Okay, so again, the same formula, we have force of BC all over the area of BC. So, the force in BC would be 26 kilonewtons. So, we have 26 times 10 raised to 3 newtons. Okay, all over, okay, pi, the diameter in BC is 0.4 or 40 millimeters. That should be 0.04 squared all over 4. Pi d squared all over 4. So if we get that, the answer should be what? We have 20.69 times 10 raised to 6 pascals, or since that is times 10 raised to 6, we can call it 20.69 megapascals, MPa. Okay, so that's the stress that is being experienced by the member BC in our problem. Okay, and lastly, of course, we have to get the stress in CD. So we have the stress of CD. We have PCD all over ACD. The same. So you have FCD, the force would be 21 kilonewtons. So 21 times 10 raised to 3 Newton all over pi. The diameter is CD, the same is 20 millimeters, but in meters, that's 0.02 squared all over 4. So if we do that with our calculator, the answer would be 66.85. So we have 66.85 times 10 raised to 6 pascals, or that would be, since times 10 raised to 6, megapascals. So here are the stresses, the normal stresses that AB, BC, and CD are experiencing. Okay? These are the normal stresses. How about the elongation? The total deformation. It says here, the total deformation. So in order for us to really solve this, okay, so we have to, I almost forgot, the value of E here is 70 gigapascals. Okay, the modulus of elasticity of this object is 70 gigapascals. So, the total deformation, we have already solved the stresses. How about the total deformation? The total deformation is solved by getting the deformation in AB plus the deformation in BC and the deformation at CD. So, first of all, we are going to get the deformation in AB, BC, and CD. So, it's very simple. In our formula a while ago, that's praise the Lord anywhere or everywhere. PL all over AE. So, we have deformation AB. We have PAB, of course, length of AB, of course, and area of AB, of course, and then the value. Same material for all. It's E. It's the value or the modulus of elasticity, which is 70 gigapascals. Okay? So, we already know the force in AB. So, the force in AB, it's 10 times 10 raised to 3. That's Newton. And the length of AB, according to the figure, okay, the length is 0.5 meters. So, you have 0.5 here. I will not, again, write the units for simplicity. And also, the area of AB. We have already seen that here. We have pi 0.02 squared all over 4 multiplied by E, which is 70 GPa or gigapascals. So if we write that in our calculator, that must be 70 times 10 raised to 9. Okay, 70 times 10 raised to 9. And what unit do we get here? Okay, so what unit we are going to get here? Well, of course, it is already in terms of what? We can get it if we analyze it. Okay? So, let me just show you what are we going to get here. So, you have 10 times 10 raised to 3, 0.5. Just checking if we are going to get the answer correctly. 0.02 squared all over 4. Then we have 70 times 10 raised to 9. That's gigapascals. So we already have 2.27. Okay? So 2 or 2.3, let's say. So let's say 2.3 times 10 raised to negative 4. It is in terms of meters. Because we already have converted all. This 0.5 is in terms of meters. This 0.2 is in terms of meters. Pascals will cancel. Okay, so this is force and this is pascal. So therefore, we are left with meters. So if we are going to convert that, okay, in terms of millimeters, so you have 0.23 times 10 raised to negative 3 meters. And times 10 raised to negative 3 meters would be actually what? In terms of millimeters, because of this times 10 raised to negative 3. So it would be 0.23 millimeters. Okay, because of this. Okay, so the deformation for AB will be 0.23 meters. Okay, so now for the elongation for BC, okay, we have PBC, of course, and length of that BC all over the area of that BC and the E, which is still the same E because we haven't changed our material, is still the same. So PBC, or the force experienced by BC, is 26. So you have 26 times 10 raised to 3 kilonewtons multiplied by the LBC. It's not the delivery service, or the that's the length of the BC. Okay, the segment BC. So it's 0.75. So you have 0.75 meters all over. Again, these are all in meters. So AB, or area of BC, so that would be pi 0.04 as we have solved a while ago, and then 70 times 10 raised to 9 gigapascal. So repeating again the process, whatever we get here will be actually what in terms of meters. So if we get this, this would be 0.23 millimeters. So it's actually 2.3 something in your calculator, but if you're going to convert it into millimeters, it's not 0.23, it's 0.24. 22, I mean. 0.22 millimeters. Okay? It's very, 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 very short, but in terms of study of strength of materials, that's already significant numbers. So, and lastly, we have to get the deformation in CD. Of course, that's force in CD, the length of CD all over the A of CD, and then E. So, the force in CD would be what? We have here the force of CD. As we can see, it's 21 kilonewton. Okay, and the length of CD from C to D is 0.5 also. So you have 0.5 in terms of meters. And the area of ACD is the same as what we have solved a while ago here. So that's pi 0.02 squared all over 4. And then we have 70 times 10 raised to 9 as the modulus or value of E. So the value of CD here, if we solve this in our calculators, we have 0.48 millimeters. Okay, so the total elongation will now be, okay, we have 0.23 millimeters plus 0.24 millimeters plus 0.48 millimeters. That would be 0.90, ito 47, 94, 93, 0.93 millimeters. So let us check. So that would be 0.23 plus 0.20, 22. It's 22, guys. It's not 24. 0.48. So that's 0.93. So this must be 0.22. Okay? This is 0.48. So the total elongation is 0.93. Therefore, the total elongation is 0.93 millimeters. So that's how we get our value for this. Okay? So that's only for number 1. Okay? So we also have another problem, number 2, and I think I'm going to discuss this in continuation of our study about strength of material. So I'm going to solve number 2 and number 3 on the next video. So if you find this video helpful, please don't forget to subscribe and share it with your friends. Okay, and again, this is Engineer Yuji Abat. This is only a part 1 of the stressed problem that we are going to solve for the strength of materials. Thank you so much, guys, and have a blessed day.